it's not the easiest thing to do. But a starting place is privacy and confidentiality in the public blockchain world. So there are a lot of cryptocurrencies that incorporate privacy and anonymity techniques. So you can see some up there. But certainly users don't agree on the best way to handle privacy and confidentiality. So CoinDesk did a poll asking which cryptocurrency would you use to send a transaction you do not want anyone to know anything about. Interestingly, most people chose Bitcoin, which isn't necessarily what I would have picked, but you know, this comes from the fact that the exact privacy and security guarantees are not explicit in these crypto systems, right? If I asked you to tell me exactly what properties Monero gave you, you might have a hard time. I mean, I would certainly have a hard time. And so this has led to some misunderstandings about these guarantees. So there have been, you know, a number of papers. I guess you can't really see them that clearly. But just essentially analyzing, say, anonymity or lack thereof with regards to some of these blockchains. And this mostly comes from sort of confusion about the definitions. And one of the big things and big problems people have with this blockchain privacy and confidentiality is transaction visibility. So are you guys familiar with this? Raise your hand if you've seen this kind of thing before. So for those of you that haven't, the basic idea is the following. So you can't really see this on the projector that well, but this is my credit card transaction history from the beginning of March. And so if you look through the transactions, you don't know it's me, you're just trying to figure out, like, who is this person? So those transactions that I pointed out correspond to a snack machine in the South Bay. So you can probably guess that I worked out there. There's a Mediterranean restaurant in Sunnyvale. So another point of information. There's a transaction with the Fujitsu cafeteria, so you can probably conclude at this point that I work in Sunnyvale and possibly at Fujitsu. I have grocery and gas in Redwood City, so you might say, aha, that's where you live. I have a weird payment to the Stanford gym. Thanks, Arno. So I have a payment to a Redwood City gastropub, and so Uber's around that night, so you can probably guess that I was out drinking there. So just from my transactions over a few days, you learned, you know, a fair amount about me. And this might not totally de-anonymize me, but if you had my transactions over the course of a whole month, you could probably pinpoint me down to just one person. And that would be the case for probably most people. So in general, you know, individual transactions might not reveal much, but an entire account's history might. So some mitigation ideas around this. So lots of people will just say, why can't we use different identities? Or in the case of Bitcoin, like Bitcoin addresses for each transaction. So for Hyperledger at least, right, we're using a permission blockchain. So how do we handle the fact that we may need to show we have certain permissions in order to perform certain blockchain actions? So this requires kind of other techniques if we want to randomize, say, the identities. And another thing people often say is, well, just use, you know, insert your favorite zero-knowledge technique, your favorite snark, your favorite star, whatever. So this is great, but it's very expensive computationally, as anybody who has used Zcash probably knows. And that might hide your identity, but, well, even if we have fully zero-knowledge transactions, the mere fact that transactions exist in certain patterns could at times break privacy and confidentiality. So here's an example. So I have complicated financial DLT alpha and complicated financial DLT beta. And you can see that they have very different transaction patterns. And if I'm looking at a blockchain and just looking at the transaction flow, I can tell whether T alpha or T beta happens, right? Just by looking at the transaction flow. And this might be an even bigger problem if, say, specific banks have specific ways of doing transactions or things like that. You might be able to de-anonymize and learn a lot about kind of the transaction history. So all of this kind of falls into a general idea, which is a bigger cryptographic paradigm called side channels. So roughly speaking, this is when you can learn something about encrypted data, even though you only see the data in encrypted form. So this comes from things like timing of things, transaction patterns. And more traditional cryptography, this might be power consumption attacks or things like that. And I've just listed a bunch of ways that information can leak. So it turns out this is a fairly old idea, but blockchain gives a much bigger attack surface. So how many people have seen the movie Wall Street? Most people? So do you remember this scene? I guess you can't really see the script, but this is the scene where Bud Fox tracks down the plane, right? Tracks down the rival executive's plane and sees where it's flying. And essentially from learning about a rival executive's flight plan, Bud Fox and Gordon Gekko can infer a huge deal is going on, and they can profit off this huge loop like they do in the movie. So for blockchain, the fact that transactions or hashes of transactions are posted in a common place might give competitors lots of information that they can use to adversely affect you if you're not careful. And this sort of thing does happen in the real world. So it turns out smart finance people track executives' social media profiles and things like that to see where networks are made and to try to guess what the deals of the future are. So with this in mind, this kind of gloom and doom, you might ask, how can we possibly build secure blockchains? I've spelled out a pretty impossible picture. So some suggestions, and I'll go into these in more detail as we go through the talk, are to clearly define your adversary or your threat model. So what exactly are you trying to protect against? You need to know this very precisely when you want to build a secure blockchain. So you also need to define what security means. In some cases, you're okay leaking transaction patterns or certain information about the transactions. You just, okay, whatever, it doesn't matter. So you need to quantify what is okay for someone to learn and what is not. You need to use appropriate tools. There have been a couple of unnamed cryptocurrencies that have, say, tried to invent their own cryptographic hash functions and failed miserably. So don't be like those people. And if you are stuck, ask someone who has a lot of experience in the field. So I guess I'll go into some detail on each of these. So how do we define an adversary? Are people familiar with kind of a cryptographic definition of an adversary? Some people? Okay. So an adversary is a hypothetical entity who attacks your system. So this is kind of a generic attacker on blockchain in this case. And our goal when we're building these things and we're analyzing them is to show that it's hard somehow for an adversary who's bounded by certain characteristics to attack a cryptographic system. And it's very important to kind of model these adversaries correctly. So you can think of this as picking the right attack model. If we make the adversary too strong and we give them too much power, we sacrifice efficiency in our blockchains. If we make them too weak, well, they're more powerful than what we assume they are, we probably don't get security at all. It's obviously better to be too strong than too weak. So kind of if we look at this in the case of blockchain, some adversarial power options are, we can define an adaptive blockchain adversary. And what this means is the adversary can actively and adaptively control up to some k fraction of nodes on the network. So in the real world, this would model like, if I have a permissioned blockchain with n nodes, an adversary is capable of hacking some of those. The system moves along. So maybe there's like one critical node that really can't fail for some reason. An adversary might be able to direct big hacking effort that can break it down, and that's what this sort of assumption models. But there's also a selective adversary model, and in this case, the adversary kind of has to choose which nodes it corrupts at the beginning of the protocol. So in this case, an adversary kind of controls some nodes which it picks in the beginning. And this kind of models an evil coalition in real life, right? So if I'm a bank and I'm on a banking blockchain, and I'm worried about these three banks' collusion, maybe they play golf, the CEOs play golf every Saturday, and I'm worried that they're going to strike a bad deal against me. So that's what this kind of models. Is that clear to people? Awesome. So we can also make assumptions about what an adversary can do with network communication. So kind of the most standard assumption is that an adversary can see all blockchain communication. And I want to note that just because an adversary can see communication doesn't mean that they can see communication in the clear. This doesn't prevent people from encrypting information. But if I issue a transaction to, say, Brian on the blockchain, it just means people can see that encrypted flow, right? We can also assume that kind of an adversary knows when a message is sent, but doesn't know all the characteristics about the traffic. So maybe if we're only posting hashes on the blockchain, this might be a realistic model, right? Because if we're only setting a hash, well, presumably that doesn't leak any information about the transaction. We can also assume that the adversary doesn't see messages that are not to or from a node controlled by the adversary. And this is a kind of unrealistic case, but when you talk to, say, certain people in spots in the financial industry, they'll say, oh yeah, we have a direct cable going from this guy to this guy. So it's totally okay that we assume that no one else can see it. So that's kind of how to define an adversary. Or it's not complete, but if you're thinking about privacy and confidentiality on a blockchain, these are the kinds of things you need to think about. So now for security. So if we want to define privacy and confidentiality security, let's start by thinking about a typical cryptographic definition. So in cryptography, we typically define security as a game between an adversary, who's intuitively the attacker, and a challenger, who's a person that sort of sets up the game. The game is set up, so the adversary wins the game, sort of, if and only if they break some security of the protocol. And I'll give an example of this in a minute. And the goal of cryptographic proofs is, given some assumptions, we want to show that any adversary that can win the security game, essentially, can be used to solve some hard problem. And in traditional crypto, these are things like factoring or discrete log. Pick your favorite cryptographic assumptions. So we can use this framework for blockchain too. So here's kind of an example of a blockchain security game that I just drew up. It's very basic, but you can see the intuition from it. So first, we're going to let the adversary choose some nodes of the blockchain to control. The adversary is going to have the opportunity to observe and potentially interact with normal blockchain flow. And then a node that the adversary doesn't control is going to issue some transaction that doesn't involve the adversary. And there will be some entropy in choosing this transaction. And then the adversary has to say guess some fact about the transaction, and they win if they guess correctly, and they lose otherwise. Does this kind of make sense to people? So what this does is this kind of game-based security notion can give us meaningful guarantees about blockchain security. So we can say things like, if the adversary is X, Y, Z, then they provably cannot learn alpha, beta, gamma under sort of normal blockchain operation, whatever that may be. And I see a lot of puzzling on people's faces. These games get very complicated. So how on earth do we possibly prove things about them? How do I show that? in this game, then you can break security. So we're going to simplify games using an ideal model. And I don't want to dig too deeply into this because it starts to get really technical. But the basic idea is we're going to design on paper an ideal system of the trusted authority. So here you can see Brian, Jonathan, and I are trying to settle some contract or deal or something, and we're using Dan Monet as our trusted authority. So in this system, if you do have a trusted authority, many security properties follow training. So it's very easy to see how things flow, it's very easy to see who sees what, and it's easy to analyze privacy and confidentiality guarantees. So what we're going to do is we're going to use cryptographic proofs to show that any attack that kind of works in the real system also works in this toy system, in this kind of ideal model. So if we show this, then we get the privacy and confidentiality properties of the ideal system. And so kind of, yeah, that's a lot. It definitely is. And I would say, though, that if you care deeply about privacy and confidentiality on your blockchain, and you don't have the expertise yourself, you should consider hiring someone who spent a lot of time at school in it. So hire a cryptographer, I would say. But luckily for us, there are plenty of tools for blockchain security. Lots of pre-existing blockchain tools that you don't have to build for yourself. So I will say that current tools are generally far behind what we actually want for a production-grade system that needs very strong guarantees, like some of the things I talked about earlier. But if you need not too strong privacy and confidentiality, what we have today is probably good enough. So in the permission world, there are a bunch of different tools. So if you're familiar with Corda, they have some support. If Enterprise Ethereum has support for snarks, maybe some of you are familiar with that. So Fabric has a nice technique called channels that I'll talk about more that enable privacy-preserving protocols with a lot of customization. Sawtooth has this nice thing called private data objects. And Indy, if you're all are familiar with that, they have a great identity toolset that helps enable privacy. So for some specific Hyperledger tools, I mentioned some of these before, and I'll shamelessly plug the CryptoLib. With the caveat that many tools here are still very new or in development, and you can't really use all of them for production yet. So I'll start with channels and kind of explain how they work. So channels are a subnet or sub-blockchain, essentially for a subset of blockchain participants perform either confidential transactions. So the basic idea is that the nodes who are not on the channel shouldn't be able to figure out channel-specific information. I like to think of this as not exactly, but somewhat like a permissioned version of Bitcoin's Lightning Network. How many people are familiar with Lightning? Most people? Awesome. Channels still require a good amount of development to use correctly, so you're probably not going to take them right out of the box and fit your application. But this kind of primitiveness is really nice because it gives you a lot of flexibility. So kind of the typical channel flow is essentially the following. So I kind of have it on the diagram here. So what you're going to want to do is you're going to want to take some state, you're going to want to move it to the channel with some set of participants, and then you can kind of perform transactions or operations, or whatever you want to call it, on this channel state. And then at some point, you probably want to move the final state back down to the main blockchain. And what you want is you want to be able to prove that kind of the transition from state to final state happened appropriately. And you also don't want outsiders to have information on internal states between the first state and the final state. Does that make sense to everybody? Awesome. So the next thing I want to talk about is private data objects. So these are in Sawtooth. The basic idea is that we want to run all blockchain operations that need privacy or confidentiality in a trusted enclave. So this is a part of the CPU that can't be kind of modified or observed, and you're not supposed to know really what's going on inside, even with physical access to the CPU. So how many people are familiar with trusted enclaves or SGX? A few people? Okay. So the point is that even the host of a blockchain node, like someone who can physically touch the CPU, can't sort of look inside the enclave and find out information about private transactions.
So is the data also encrypted?
It depends. Sometimes, yes.
It could be.
It could be, yes, absolutely. So you could certainly encrypt code and then run it in the enclave.
And then can I encrypt the op?
Yeah, you can absolutely have encrypted enclave, right? So the enclave gives you essentially attestation for free. So the enclave can just tell everyone that, hey, this is a valid transaction. I'm not going to give you the transaction. I'm not going to tell you anything about it, but that's a valid transaction.
Does the enclave have a separate key to re-encrypt the data and for each node?
So each enclave has a separate master key, but you can have them share a key if you want. Right? There is some risk with this because if one enclave gets broken, then they all have the shared key. But there are various in-between solutions you can get to.
So as an auditor, we need a lot of validate certain transactions, certain enclave design that be accessible by third-party auditors.
So you would have to build your blockchain that way. So you could certainly build a blockchain that had the enclave, say, send encrypted financial information to an auditor, right? So that way the auditor would have the required information. And even better, you could have the enclave just tell the auditor when something broke rules. So if you told the enclave the rules, the enclave could essentially do the auditing inside itself, and then it could output something in the clear if someone broke the rules. So it gets more complicated if you have secret auditing rules, but you could probably do that too.
I think I read that there's no certain way to apply factor or meltdown act to SPX.
Yeah, so not directly, but there have been a ton of side channel attacks on SGX. This is kind of on the next slide. But you're exactly right. You have to trust the enclave and trust that it can't be compromised. My personal opinion on this is that I'm probably willing to trust the enclave for small transactions. Like my, $5 coffee is I'm okay with that payment going on an enclave, right? I might not want to buy a house or a car, but something small, right? Particularly for things like IoT use cases, right? No one's probably going to spend the time and effort cracking an enclave so that they can modify what their needs, right? Things like that. Does that answer your question?
Yeah.
Awesome. So private data objects are currently under development in Hyperledger Labs. They're not product ready, but I expect that they'll be certainly in Sawtooth and maybe even Java, hopefully in the not-too-distant future. And again, as I said, these require that you trust the enclave. So you have to trust it, say, if you're using SGX. But if you do trust the enclave, you sort of get the best possible security you can get. Perfect security modulo of these things like side channels and transaction patterns that I mentioned before. There are some drawbacks. Maybe they have to write smart contracts, code or chain code, so that it runs inside the enclave. But in general, this is becoming easier and easier. So finally, I'll mention the Hyperledger crypto link. So this is an in-progress, very early development effort aimed at creating a modular shared crypto library for Hyperledger projects. So the goal is to have a single crypto library that meets everyone's needs for stuff in Hyperledger, from very basic things to zero knowledge stuff. And the key point is we want the ability to be able to swap particular protocols, say a single line change in a config file. So if you're using ECA, you should be able to change your blockchain configuration between, say, ECDSA signatures and Schnorr signatures with a simple config change. So I guess I'm out of time, close to it, so I'll summarize. So designing private blockchains is hard. What should you do? I guess in summary, well, a good thing to do is to use well-studied standard protocols in the ways which they're intended to be used. I can't tell you how many times I've seen people make mistakes because they use a protocol for something it's not meant to be used for. The best is to get someone with a background in crypto technology. If you're interested in kind of privacy and confidentiality behind blockchains, I encourage you to get involved. There's a lot of information on the wiki. There's a ton of information on chat. So the architecture working group and the privacy and confidentiality subgroup will use these meetings. You're welcome to join. This is a topic that interests you. There's no experience required. And the crypto meetings are also every 2 weeks. So if you'd like to join, if you're interested in cryptographic protocols, I encourage you to join. Yes. So I guess that's my half hour. Thanks for your time. Are there any questions? Sure.
Just curious, if you've heard of the Oasis Labs, they're also aware that there's workshops on their protocol, when these plays. Just kind of curious what your thoughts on how that works.
I don't really know very much about them, unfortunately. Sorry. Oh, what? There's not a historic fact.
Okay, great. Thank you.
Yeah, sorry. Sorry, can you speak up? Yeah, that's a good question. So multi-signatures, aggregate signatures, and threshold signatures are particularly important for Indie, if you're familiar with it. So these are especially important for blockchains that are dominated by reads, because you don't want to have to issue an inquiry every time somebody asks for a piece of information. You don't want to have to query all the nodes. If you have a threshold signature or a multi-signature, then you can just pull that from the node, and that is sort of a signature from the whole blockchain on a particular fact. So yes, Indie uses these already, and we're planning on having support for several of these in the crypto community. I'm sorry, I couldn't hear you. I don't know who's been seeing the most attacks. So people involved with Hyperledger generally just kind of write the software. So we know if there are bugs. So I can kind of tell you where the bugs are, but I don't know, like, the bugs we know, yeah. But I don't, like, the production people generally don't tell us, like, oh, we're being attacked. So they're certainly the most fabric deployments compared to the other Hyperledger platforms. So if I were guessing, I would say that they saw the most attacks, but that would just be solely based on the number of deployed systems. Yeah, sorry, I can't give you a better answer on that.
Given that the permission is probably cheaper, less than that surface.
Yeah. So it's much harder to attack than a public blockchain, because if you don't have the credentials right away, then everything is just kind of discarded. It's true, yeah. Any other questions? I have not a clue. You're assuming a safe data center exists. I'll tell you what, it's the, I'll say the NSA data center in Utah, where they're storing all your personal information. Any other questions? Awesome. Well, thanks a lot, everybody. Thanks, sir.